We saw in DLVO theory that colloidal stability is basically a function of a struggle between Hamaker attraction, which destabilizes the colloid, and electrostatic repulsion, which stabilizes it. Occasionally, electrostatic repulsion is not enough to stabilize the colloid, and we need some other mechanism. And it turns out that we can use polymers to stabilize a colloidal dispersion. So why is it that if we take a colloidal particle and coat it with polymer chains, we can make that colloid more stable? What is it about the polymer chains? Well, it turns out that unlike DLVO theory, polymer stability, or stabilizing colloids with polymers, is actually an entropic effect, not an energy effect. So why is that? Well, the fundamental fact is that polymer chains in solution have a very high entropy. Or another way of saying this is that dissolving a polymer chain in a solvent increases entropy. We can get an idea about the size of that entropy by using a sort of crude model. So let's look at polyethylene. But for our purposes, let's just consider it the repeat unit to just be one carbon. So we have a bunch of CH2 groups linked together to make polyethylene. And let's consider a chain with N equal to 1,000, which isn't all that high. It's possible to have very high molecular weights in a polymer. Now, let's contrast what happens when we're in a solid to what happens in solution. In a solid crystal of polyethylene, so in the solid crystalline state, if we look at this, if we were to make a perfect crystal of this, we know what the conformation would be. It would be all anti. So we can draw this with a Newman projection. So if we look at the atom, so we're looking along one carbon-carbon bond. So the little dot represents the front carbon, and so we're going to have a chain, and then on that same carbon there's two hydrogens. So imagine we're looking along this bond. So our line of sight is along that bond to the next carbon. Well, the next carbon, we've got a chain and two hydrogens. Well, the lowest energy state is to put the chain opposite the other chain, so that reduces crowding. So this would be the Newman projection of the most stable conformation for every bond in that solid crystal. So if we didn't have any defects, all the bonds would look like this. Okay. So we say, how many different conformations are there that satisfy this? Well, there's just one. So one conformation possible, because every bond would be in this anti-conformation. So entropy on a molar basis, so if we look at just the conformational entropy, that would be equal to R times the log of the number of conformations. This is Boltzmann's famous equation. And we said that there's only one conformation, so this is going to be equal to R log of 1. And we know the log of 1 is 0, so that's equal to 0. So there's no conformational entropy in a perfect crystalline solid for the polyethylene. Well, what happens when it dissolves? In solution, the bonds in polyethylene are free to rotate. So we have the front atom with the chain here and its two hydrogens. If we look at the back atom, we know the lowest energy conformer will be the one with the chain being here. But we also know that we could rotate this bond and we could get some other conformers. So we can draw three different conformers. Now, of course, this is sort of a crude approximation. We know that there's a bunch of different bond angles that are possible, but the three lowest in energy would be the ones where all the torsional angles are offset by 60 degrees, and those are the three that I've drawn. So let's imagine that there's really only 3 conformers for each bond, or three rotamers for each bond. And the question is, how many total conformers are there for the molecule? So if there's 3 positions per bond, and there's approximately 1,000 bonds, omega is equal 3 to the 1,000. So that means that the conformational entropy, this is only the portion of the entropy that's due to conformational changes, is equal to R log omega, which is R log of 3 to the 1,000. And we can take the exponent and put it in front of the R. So we get 1,000 R log 3. And if we plug that number in, that ends up coming up to 9,100 joules per K per mole. Now if we figure out what T times S is, because remember in thermodynamics we're always comparing the enthalpy H with delta S times T, so that's really the more relevant thing. If we plug that in with plugging in room temperature, we get 2,700 kilojoules per mole. This is a huge amount of energy, which means there's a big driving force towards dissolving polymers in solution in terms of entropy. So now let's see how this plays out in terms of colloidal stability. So we have 2 silica colloidal particles, and they're both coated with polymer particles, or polymer chains. And we know that each of these polymer chains generates a huge amount of entropy as it flops around in all sorts of different conformations. But what happens as these 2 colloidal particles approach each other? Eventually, we're going to get into a situation where the confinement between the 2 particles is going to reduce the amount of different conformations those chains can adopt. And that's going to decrease entropy, which of course, if you have a decrease in entropy, that is going to give you a penalty in terms of Gibbs energy. So it's going to be unfavorable for the particles to get too close together because we'll be losing conformational entropy in our chains. So this leads to repulsion between the 2 particles, and it's an entropic repulsion. Because crowding the polymer chains would result in an increase in energy, and that's what prevents the 2 particles from approaching each other, we call this steric stabilization, where steric is just anything to do with space or crowding. So steric stabilization is caused by entropic repulsion of the polymer chains.